of the idea. I can't remember how far I went with it. Was I talking about the people in Florida yet?
No.
Not yet? Okay, let's do that. And I've done this once before. Chubby Dude, I don't know if you remember. Where it said if you're a god and you can reach down and you can make people older and younger, the standard deviation would grow. That's why Chubby-Chub's theorem works. No matter how your standard deviation gets bigger to catch a certain percentage of the data. You guys sort of remember that? Okay. So let's do the same thing again. Let's have this Florida at a population of people's ages. Here's the mean in the middle. And this is if I talk to individual people at a time. I say, how old are you? All right, how old are you? 2.5. Okay, how old are you? 90. Okay. Right, and then what if instead, so this has a certain mean, this has some certain standard deviation. What if instead I talk to 10 people at a time? I said, you 10 people, figure out your average age. And they're like, who the hell are you? So I'll give you $50. All right, cool. And they do it, right? Bill Gates is funding this. And so I do that for every possible group of 10 people who are in Florida. Are you with me? The most likely thing that happened, if I take 10 randomly chosen people, what's the most likely average age they would have?
56.
That was way more specific than I imagined would happen. If I take 10 people, is it likely that I'll get these 10 people? If I randomly select, what is the most likely kind of thing to occur?
Somewhere in the 50s.
Somewhere by the mean.
Let's get out of the specific ages. I'm not sure. Yeah, somewhere near the mean. Because what's going to happen is I got a few people there and a few people there, and they average out. And that's why it's an expected value. The mean is the expected value. If I take 10 people, or 12, or 20, or 800, I expect their average age to be close to the actual average. Let me just let that sink in. I mean, we've been actually talking about it since almost day one, this idea. The larger the sample, the better, but still, if I take a sample, I expect it to be close to the average age. That's why it's so it's more unlikely that they would be some extreme age. What's the probability I would get 10 people and their average age is 102? Probably very unlikely. It's really unlikely for me to pick one person randomly and they're 102 years old. That would freak me out. If I pick 10 people randomly, you and you and you and you and wow, you're all old. How old are you? 102, 108, 192? Well, yeah, dude. So let's say we take samples. In this case, you take samples of size n equals 10. Now, the first thing I want you to realize is what I just said is important. The highest peak on the new picture. This picture was made how? How did I make this picture if this was official? Not me just making shit up, but I actually went out and talked to people. How would I make this picture?
By drawing it on the board.
How would I get the data for this picture?
Ask questions.
Asking individual people.
I love it. The key word is individual. How old are you? Okay, I'll plot your age. How old are you? You're the same age. I'll put you right above her. And eventually I get all this. So this is the most likely younger and this is the most likely older person. You with me? Those two peaks there. Twin peaks might be coming back. I don't know if you know. But when I pick 10 people at a time, and I'm going to plot their average age, and I say, you 10 people, figure out your average age, and then tell me I'm going to plot that. So now the highest peak should be where?
In the middle.
In the middle, because that's where most of the random sample should be. Any random sample should be close to that. It's going to be very unlikely for them to be out somewhere crazy. But only 10 people. So what's the second most likely thing to happen here? So the most likely thing is a mixture from both. The second most likely thing is, since this is a big peak, maybe I'll get a bunch of people here, maybe just a couple people there. So here's what the picture's probably going to look like. And here's the next thing I've got to ask you. If I take 10 people at a time, and then average their age, and then average all the groups of 10 people's ages, how will it relate to this?
It will still be in the middle.
So if I took everybody individually and I took your ages and I calculated the average, and then I took 2 people at a time, calculated your average, and then I averaged all the 2 people averages, would that be any different? Of course not. It's the same people, right? So the average, now watch it, you ready? This is the average of individuals. the average of all these sample means. So it's got a little X bar subscript. It's not the average of the individuals. It's the average. Right? It's the average of all the sample means. So I really want you to understand. If I take 10 people, let's pretend we're in Florida. 10 people in Florida. You tell me your average age. Our average age is 3. Okay? So I put you right there. Oh, why you sound Mickey Mouse? And then eventually I get this whole picture made, and what's going to happen is I'm going to get the largest peak around there, and then I'm going to get another little peak there, maybe another little peak there.
You do that on purpose?
Well, it depends on where your mind is. So I guess you answered that question. So this is that. This is kind of like that, and this, of course, is there. Most of the people should be right in the middle. You with me? Try to get past it. Just trying. I would be worried about the individual if that's what you're talking about. All right. You need to see a doctor. Another important thing. So they 10 people they're 3, 10 people they're 48, 10 people they're 39, whatever, right? I average all those averages. I'm going to get the same number I got before for the average, of course. Just because I do it 10 people at a time, the average age for Florida is not going to change from what it was. Does that make sense by itself? So whatever the mean was is what it still is. The mean of the individuals is the same as the mean of the means of groups of people. Yes, ma'am?
So basically it stays the same because you're still calculating all the same numbers.
Exactly. I'm still including all the same people.
Mm-hmm.
Right? You're just doing it 10 people at a time instead of 1 person at a time. Beautiful. What she said.
Mm-hmm.
Okay. What else is true here? What about the standard deviation? Is it the same? Are the data points the same distance away from the mean on average?
Yes.
Most of the data points are where now? Right on the mean. So is the distance from the mean to the data points the same that it used to be?
No.
Because most of them are right on top of the damn thing, right? So the standard deviation is now smaller than it used to be. And that's what we talked about last time. It should be less likely to get extreme values. It is less likely to get somebody who's 102 than it was before. Okay, maybe. So if I take this to an extreme, if I take it, let's say we take a group of 50 people. My picture now will look like this. Basically, without fail. It'll look something like that. Now my standard deviation is damn small, right? And what else is true about this? It looks very, some word important statistic. Normal, right? I know it looks like a really skinny ass bell, but it's still a normal curve. Normal curves can be fat as hell, or they can be really skinny. So the magic number, there's something called the central limit theorem. Okay, so this is important. So what it says is, as n increases, our sampling distribution. Let me stop right there. This is the sampling distribution of sample means. Here I've plotted individual ages. Here I'm plotting groups of 10 people's average ages, right? So that's why we call this the sampling distribution of sample means. And all that means is I'm graphing sample means. So as n increases, our sampling distribution of sample means gets more normal. Which implies there's actually a way to measure the normalcy, and there actually is. Something a little bit beyond us, but we understand what that means. It gets more and more symmetric, it's more and more bell-shaped. 2. Mu sub x bar equals mu. And 3, we know that sigma gets smaller this is exactly how it gets smaller. The new standard deviation for groups of people or things is now the old one divided by the square root of n. So the more and more people I pick for each sample I take, if I take 100 people, it is incredibly unlikely that they're going to all be having an average age of 1. So that's why this is so tiny back here at 1. And basically the whole damn thing is here with very few people out there. If I take 100 randomly selected people, they really almost can't be at an extreme. They almost have to be right at the mean. But it's still possible. If you have 100 people that are 1 year old, you could pick them. But how likely is it if I just do it randomly? Remarkably unlikely. That's why it's so tiny down there. And of course the other way, for the 102-year-olds, right, or above. Okay. So let's do this. A little more theory. It's going to become a little more concrete, and then we'll get really, really concrete with exactly what this means for you and your work. So let me give you my most colorful picture. Well, some of them came out. Depends on how my printer's feeling. Real quick, I want to show you something. While that thing warms up, I like this. I don't know if you guys know the Binomial.
Oh, yeah.
So I don't know if you know, I've never gotten called by a pollster, like for Gallup or something. I don't want to be a part of that study. Become a data point, sir. Oh, thank you. And then here's something. Whoa, look at all that. That's awesome. It's a study about life after death. There's actually been a huge study about the possibility. This is not anything religious or heaven or anything. This is about how much awareness there is. And this is related to people that were clinically dead and memories they had during that time. You've all heard the tunnel and all that stuff, but this gets a little away from that into general weird things. And again, just to remind you guys, I love the last one. What was it? So all I do is type in the word study. Type in the word study and then set it to the past week. And you normally get these brand new kind of studies that are done. It's kind of nice. And very often I'll pick something out of there to make some problems off of. But let's get to this here. Let's make sense out of this thing. So the basic idea here is you understand. I just put the numbers 1, 2, 3, 4 on a slip of paper, put them in a hat, and if I had people grabbing it out of there, we know exactly what the mean would be. Right? The mean would be 2.5. Makes sense. So if I had many people pick a number out and put it back in, I average all the numbers, it should be somewhere close to 2.5. Is that cool? Because there's no preference for 1, 2, 3, or 4. That feels like a 2. No, I mean, they're the same slips of paper. And of course, they all have the same probability. They're all equally likely, like I just said. So does everybody understand this table here? Right, each probability of 1/4, because there's 4 numbers. Right? This sounds like the very beginnings of chapter 4, so this is nice. Standard deviation, I calculated that the way you did on the quiz you just took. Right? You can do it that way, or you can just type 1, 2, 3, 4 in your list and do 1 bar stats on it, and you'll get 1.118. So that's the standard deviation for that situation. Okay, how are we doing so far? Nothing too major yet. And of course, this is what it looks like. It looks like a uniform distribution because they're all equally likely. So does that look normal at all?
It looks like a big gray block.
Yes, a big gray block right now. It's supposed to be blue, but my printer decided if you have blue, you didn't win a prize, I'm sorry, but you won that. You won blue. Nothing to write home about. All right, so what we do, this basically represents a very small Florida with only 4 people in it. Yes?
Do you want to fix the camera?
Oh, yeah, thank you. Please, everybody help me with that. Remind me. I want to be further away somehow. Poor little dude. Oh, yeah. Go ahead. Thank you. Here's the battery.
Thank you.
Thank you, miss. I don't have any TA money for you. Sorry.
That's okay.
So it's not a kind of state part.
It is. 2
So
points
if
extra
I
credit.
just have people, so I'm taking samples of size 2 now. Instead of 10 people from Florida, I'm going to take samples of 2 from this hat. So what could happen? I'm doing this with replacement. Why would I do this with replacement, do you think?
Because then it makes a better binomial distribution, right?
Yeah. What's the main thing with binomial? The probabilities in a binomial distribution are P and Q. If I took one out and threw it away, and it's not necessarily even binomial, but if I took one out and threw it away, all the probabilities change. All my work becomes so much harder. And normally we're dealing with a pretty big population here anyway, so I can use the 5% kind of, it doesn't matter which way you do it rule. Okay? All right. Maybe. So we're just allowing for the possibility I could pick the same person again. In this case, the same piece of paper. So if I pick 2 slips of paper, one and then pick another one, what could happen? I could pick the same one. I could pick a 1 and then a 1. I could pick a 3 and then a 2. I could pick a 4. So I put all the possibilities here. So this is a more manageable problem than everybody in Florida, right? That would be kind of a large chart. So it's a little more manageable size. And this is actually what the Section 6.4 homework is going to entail. They give you several examples in that section, so that'll help you figure it out yourself. But here's a beautiful example. So sample 1-1, what's the sample mean? 1. Sample 1-2, what's the sample mean? 1.5. Right? You just add them up and divide by 2. Do you guys see where all those numbers came from? So these are all the possible picks of 2 pieces of paper, and these are their sample means. So now, that first picture, the gray block, is like this. The second picture is like that one or this one. Same kind of idea. I've started to pick samples of size. So now if I plotted all the averages, notice what's the most likely average?
2.5.
2.5, which makes sense in a way. It doesn't have to be for a small sample, but because this sample was 1, 2, 3, 4, nice and symmetric to begin with, that's going to happen. And now if I plot these, so 1 occurs once, 1.5 occurs twice. If I plot them, I get this here. Now does that look more normal? Yeah, it looks really normal, right? If that was back in chapter 2, we would have said that's normal. If you constructed this histogram. You with me? And what's really important here is if you take these means, and here, this is a good review. Take a minute and just make sure I'm right, because I made this thing a few semesters ago. I could be wrong. Put these in the yellow boxes, put them into list 1. And just double check me on my standard deviation. Everybody with me? Put those sample means. That's your new distribution. Are those sample means? Put that into list 1 and calculate the standard deviation for that. Hell no. Definitely not, because there's 4 of them that are right on top of the mean, right?
1.75.
And then there's fewer that are a little bit further away. So it's going to be, who knows? And 1 is 1.5 away from 2.5. But it only happens once, right?
Yeah.
So it's going to be some average of those distances. That's what the standard deviation is. So it's going to be somewhere in that range. Sounds about right. Yeah, what do you get?
1.75.
So 1.75. Let me make sure. How large is your list?
1, 2, 3, 4.
Okay, that's a problem. So if you're making a list, you should have in there a 1,
Oh.
you should have in there 2 1.5s. You should have, I mean, well, how large is my list? How many things are in my list? 16. So if you put all 16 things in,
I got
Okay.
7, 9.
that's much better. I don't have to throw out the 100-year-old theory. So repeats are definitely considered. Because if I have the mean repeating a billion times, that standard deviation should be really freaking small, if not 0. But if you only put it in there once, it could be huge now, because the other ones could be way far away from the mean. So you have to put repeats in there. They're valid data points.
So it's 2.5?
No. So, let me see.
So you would add 1.5
No,
to
you,
2.5.
No.
You make it into a list and you put everything in yellow in there, right?
Yeah.
Oh, yeah.
Okay, so I did that. Everything in yellow is in there and it's 2.5.
No, not the mean, the standard deviation.
Oh.
That's the problem. Okay.
Oh,
There it is.
0.7905.
Cool. And it's a sigma we're using, right? Not the S one. We're using the sigma one. Why are we using the sigma? Sigma's for what? Sigma's for population, right? S is for sample. So why am I using sigma? Did I leave any possibilities out? So I did. Did I?
No.
I hope I did.
No, good.
Somebody's looking at me like, yes, you did. Those represent every single thing that could possibly happen. So that is a population of picks. Are you with me? If I actually had 3 of you pick, that would be a sample. This is a population. It's not big, but I only started with 4 numbers, so hey, it's not going to be big. That's why we use the letter sigma for it, because that's the actual population of all the things that could possibly happen. How we doing so far? And what's really neat is if, remember what was the standard deviation? For just the 1, 2, 3, 4 by itself, just one pick was 1.118. How big of a sample did we pick each time? When we went down here for the second part. How big of a sample? How many slips did I pick out at a time?
2.
2. So if you take 1.118, type that in your calculator, divided by the square root of 2, what do you get?
0.7905.
The actual standard deviation that you got later, right? So that's the formula. That's how the standard deviation changes. The new standard deviation, what I call the new one, stop cooking. Sticky keys, man. The new standard deviation. The standard deviation for groups, that little sigma with the X bar, that's equal to the old one divided by the square root of the sample size. So if I would have taken 3 slips of paper at a time, and done this whole thing again, my chart would have been way freaky big. But my new standard deviation would have been 1.118 divided by square root of 3. Okay, so everybody semi with me. And the fact that it gets smaller should make sense. It made sense to us even last time when our brains were semi-fried. We were trying to get out the door and Jeff wasn't letting you. Right? And I said, it kind of makes sense. If I take a group of people, most of them should be close to the mean. So the overall standard deviation is definitely going to get smaller. That formula just tells me exactly how much smaller. Kind of nice. Unfortunately for us, again, the mathematics behind this is a little bit beyond us, or not. Maybe some of us could do it. So I'm not going to be able to show you where this comes from. That would be like stats 2 maybe, or 3. Right? But it makes sense that it's getting smaller. That part makes sense. How are we doing so far? Okay. Poker faces. All right. So let's get to a very, very concrete, what the hell does this mean for my homework, Jeff, and what are you going to do to me on a quiz or a test? This is what I'm going to do to you exactly. This is exactly the kind of problem I want to give you. Here we go. creativity is kind of buzzed out. So we're just going to have, these are numbers. I don't know what they represent. So part A would say this. We pick one item. This could be book prices. Let's give it some kind of a meaning. This is maybe like textbook prices. Is that cool? Obviously it isn't, considering it came with what it was after it came with the numbers. But just to give it something, it sounds about right, unfortunately. Maybe. Maybe it's a little high, but still, it's getting up there. If we pick one book, one item, what's the probability that the price is more than $230? That is nothing new. That is not a new thing. That is old. That's section 6.3. How do I know it's not new yet? What tells me that I'm going to be doing this kind of stuff?
Because we need to take a sample of the sample.
Yeah, if I take a sample, then my standard deviation changes. In fact, here, how many things am I picking?
1.
So divided by square root of 1, it's the same standard deviation. Nothing changed. So this problem is old. How do I do this problem then before we do the new stuff? Part B.
Draw
Draw a picture, and the middle goes 211.5, and take the ball out. And what's the point I'm interested in?
230.
230. So up there somewhere, and I want to know greater. So this is what I call a classic z-score problem. We're going to tweak this thing several times over the next couple weeks. This is our first tweak to it, right? It hasn't even happened yet. We're doing an old problem still. So I'm making a z-score out of this. How do I set that formula up? X minus the mean over standard deviation. So it'll be, what goes first? 230. So always my data point minus the mean goes second always. And I know my z-score should be positive or negative. Definitely should be positive. So if you get a negative z-score there, you just know you did something wrong. Don't just keep going forward. You know it should be positive. It's up there. So 230 minus 211.5 over 47.12.
0.3926. 3926.
Yes, okay. I want verification. 3926, so 39, rounding it to a couple places. Look that up in the chart. What do you guys get? And of course, I know I can do all this work. Why? I know I can use that chart because it's normal. Exactly. Now, to be honest, I could do all this work up to here, even if it wasn't normal. The z-score doesn't care if it's normal or not. This is important, actually. The z-score doesn't care if it's normal or not. I can find a z-score for any distribution. Give me mean, standard deviation. I don't care what it looks like, I can make a z-score. How far away from the mean is. The z-score becomes those probabilities there on the chart only if it's a normal distribution I'm working with. If it's some other distribution, who knows? The best I got is chubby dude. And he ain't much. I'm sorry. He's a lot, but compared to this, ain't much. So there's 0.39, and if I look that up, what do you guys get?
0.6517.
6517. So the actual area I want, yeah, 1 minus that, so 0.3483.
Yep.
So about almost a 35% chance. 34.8% chance we'll get something above a textbook costs more than $230 if those numbers are true. All right. Now, the reason we were able to do that whole problem is because it was normal. So I can get all the way down to an area and be done with it. There's a huge thing I didn't leave out of this. I just haven't gotten to yet. The magic number for most distributions to become normal enough. We're going to hear that phrase a lot. If it's normal enough, I can use the chart. What's so nice about that? It's covered in freaking answers, right? So it's nice. When can I use a chart if it's normal enough? So the magic number is not quite 50. It's actually just 30. If I get a sample of at least 30, then it's normal enough. to use the z-score chart for probabilities. N equals 30 makes it, or more, let me fill in, makes it normal enough. Yes, ma'am.
So they would have to tell us that it's normal and that it's
No.
30.
The beautiful thing is, if I would have done this whole problem and not had this word there, and just said, instead of picking 1, pick 32, you could still do the whole problem that you would say, central limit theorem says, that's normal enough. The sample size I'm picking is at least 30. Therefore, my sampling distribution becomes normal enough. So then I can use a chart.
I don't know how that makes sense though. It's weird. Because
It is weird.
N then just the number of what
Yes,
you're looking at?
but again, no matter what freakiness, we had this thing earlier. If I take a sample of size 2, this ain't becoming normal. But if I take a sample of size 100, it's almost impossible to get only people right there.
Oh, okay.
So now what's going to happen is it's going to have to congregate in the middle, and then it's going to fall off from there. So it is going to become normal enough. Cool. Now there's a lot of good questions hidden in what you just asked. How do I know it becomes exactly the normal curve and that kind of thing? And it doesn't become exactly it. It becomes close enough to it. And the larger n gets, the closer it gets. How are we doing so far? So 30 is enough to make it normal enough to use the z-score chart. Now in this problem, I didn't need 30. I didn't need 2. I just needed 1 because it was normal already. It doesn't need 30 to make it suddenly magically normal when I redraw it. Right? Okay, so here's part B to this question. Part B says, if we pick 16 books, what's the probability it's more than... Now watch this. So 2 things actually you need to know when to do this, when to make a new standard deviation. Number 1 is obviously if I take a sample, because I need an n in order for that to do anything really interesting. Right? Number 2 is the question has to be about a sample mean. So if I take a group, what one thing can I talk about them? The mean of them, right? I want to compare sample means now, not just individual books prices, but 16 book prices, their mean compared to other 16 book prices. So it's going to say, we took a sample, and it's going to ask a question about the sample mean. Sample mean question. Now, even before we do this problem, do you think the probability is going to go up or down? Notice how it's almost the same question here, right? This is for an individual book to be more than 230. And again, what's the average price? What's the mean price? 211.5. So for an individual book to be more than 230, it went down to 39% chance. If I take 16 books, the likelihood that their average price will be more than 230, will it be higher or lower than that?
Lower.
Will it be more or less likely to get 16 textbooks that are not the mean, but are actually more than 230? It'll be less likely. Now, I could go extreme. I could have done the probability x greater than 500, right? That actually have one textbook be $500. I don't think it's going to happen. Thank God. You want that? No. That's the one class you could take. I could buy half the book, right? But one textbook, it's much easier to get one textbook randomly that's more than $230 than it would be for 16. Where should 16 textbooks average price be?
Middle.
Should be right there, or close to it. So the probability that it's more than 230 should be tiny probability, should be much harder. Well, let's see if it happens. And why is that? Everything, when I take a sample, everything rushes to the middle, which leaves very little stuff outside. That's also why the standard deviation gets smaller. So the first thing I do when I see, I took a sample. What is that, Jim? I took a sample. And 2, there's a question about sample mean. Those 2 things tell me I need to do this tweak. before I do any work. So before I do anything, I don't have the right numbers. I have this number, which is okay, and why is this number still okay?
It's still the
Because it's still the mean, right? It's the mean of the means. It's awesome. This number sucks. For me now in part B, why does this number suck?
because it's too high
Too high, but it's intended for what?
for one.
For one, I love it. Exactly. This is for individual textbooks, how much they vary. I need to know how much 16 textbooks vary from each other. So really, that's all you're doing is I can't do this problem with that number. That's for one book at a time. I got 16 freaking books I'm looking at. So what's the new standard deviation going to be?
47.12 divided by the square root of 16.
Kick ass. And what's that?
I don't know.
And you know how much to take it out to and all that kind of stuff. That's been the rule forever since you first learned it.
2.945.
8.
Square root.
11.7. You guys get that? Just divide that by 4, of course, right?
11.78.
Kick ass. And then you do this again. So the only difference. How long did it take me to explain the idea? Way too long. You're like, please stop. The idea is weird and freaky, and you got to really wrap your brain around it. What does it do to you work-wise? You got to change standard deviation before you do this. So I mean, nuts and bolts. It doesn't do much to you at all. You can't use that. You got to use that. So all the work's the same. So I can even make my picture. You can make it skinnier if you want to, but it doesn't matter. It's just a visual, quick representation. My mean is still 211.5. I'm still interested in 230. I still want the area above 230. But when I make a z-score, what's that formula going to look like now?
16 minus...
Careful. 16 is just what? Just the number of things, right? That doesn't have anywhere to go in the z-score formula. Z-score formula is always my score minus the middle divided by the standard deviation. It's just that in this situation, the standard deviation is now this. So it's still going to be 230
minus 211.5.
divided by the new standard deviation. Yep. 1.57.
Yeah, 1.57.
So what's that area now? Wait, 9418? And so our answer now is 0.582. I like it. So now it's gone down to 6%. There used to be almost 40% out here. But now they've taken a sample of 16, there's only 5.8% out there. Because everything rushes to the middle. It leaves very little out at the extremes. Hopeful. All right. So to be completely honest, 6.4 is going to freak you out. I'm just going to be straightforward. And you got to look at the examples. They do some of the work for you already, which is really nice. Let that be nice. 6.4 is going to be freaky. 6.5 is this. A lot of them have like I like. Part A, where they ask you about one thing. Part B, they ask you about 16 things or 20 things, or whatever. If they don't say it's normal, what must happen?
Then it must be over 30.
Beautiful. Sample size they pick has to be at least 30. I think this book says over 30. It depends on which textbook you use. What do you say, book? I almost don't care. Yeah, they say greater than 30. Textbook I was taught from said at least 30. So, hey. So it's got to be greater than 30 in order to be normal enough. All right, so quick little word on the next, on the last section we're going to do in chapter 6. Do you guys remember that handout? It'd be so awesome if I had it. With the flipping a coin, and I had the histogram down there with the, I said probably have at most 6 heads, all that kind of stuff. Do you guys remember that? good. Somebody have that by any chance? Yeah. Oh, I got it. Yay. So this guy here. Now, that looks really normal, right? So I should be able to apply z-score idea and the chart to calculate probabilities from this, possibly. There's got to be a test. There always now is going to be some kind of test for some weird distribution. This is binomial. How do I know it's normal enough? There's going to be a test. I can't just say, is the sample size big enough? And here's why. I just got to talk a little bit about this. We'll still get out a little bit early. If I took, let's say, 35 things, but the probability of success was 0.001, what's the average? What's the mean of that binomial probability? So it's really unlikely to get a success. It's very unlikely to get a success. And I take 35. That's greater than 30.
It's 0.035.
Okay, yeah, you just multiply that by that. So the mean is going to be 0.035. So where should the tallest bar be close to? And the best I could do for, of course, a binomial is it's going to be right near 0, right? So does this look normal?
No.
So the idea seems to be that the mean has to be out far enough away from this wall. What's this wall physically? 0. And of course, for a binomial, can you go below 0? No, you can't have -4 people like my toothpick. No. What happened? What that even mean? So there's a wall there. So if n times p is too small, that's where the bar is going to be. Does it have any chance to be normal? No. So I want to pull this thing out. And what actually happens is if np is greater than 5. Because if np is greater than 5, so if it equals 5, there's just enough room for it to grow and shrink. Now the other side of the wall, there's a wall over here too. Why is there a wall right here? Because how many times have I flipped this coin? How many times was I flipping this coin? 14. So what's the most successes I can get? 14. I can't get above that. So if my mean is too big, it sucks. And actually the way I take care of that in a more manageable manner, because too big is going to change all the 10 times, but too small is basically 5. I want my average successes to be more than 5. And my average failures, if my average failures is more than 5, it's going to pull it away from this wall. So both of these together make that picture more in the middle that gives it room to grow up and come back down. If those two are true, then this binomial situation can actually be approximated using a normal distribution. Holy shit, that was a loaded sentence. Let me say it again. If these two things are true, this binomial situation can be approximated using a normal distribution. So I can calculate probabilities using the z-scores and the z-score chart. We still have a decent amount to talk about. This is section 6.6, by the way, what we're talking about right now. All right, that's a decent little preview. So we'll get into that next time. So on Wednesday, I'll have the answer key for that normal distribution handout, and I'll have the quizzes graded. Somehow. It's on tape now, so I got to do it. Thank you for that.
Yeah, no problem.
Stay